The two sets of figures should have been similar, but as the survey team moved across the park, they noticed something unexpected. The ground seemed to be heaving upwards.
And then the conclusion kind of hit me in the face. It said this caldera has uplifted at that time 740 millimeters in the middle of the caldera.
As the measuring continued, an explanation for the submerged trees began to emerge. The ground beneath the north of Yellowstone was bulging up, tilting the rest of the park downwards. This was tipping out the south end of the lake, inundating the shoreside trees with water. The volcanologist realized only one thing could make the Earth heave in this way: a vast living magma chamber. The Yellowstone supervolcano was alive. And if the calculations of the cycle were correct, the next eruption was already overdue.
Well, this gave us a real shiver of nervousness, if you will, about the fact that we have been through this 600,000-year cycle, and that the last eruption was about 600,000 years ago.
The scientists had found the largest single active volcanic system yet discovered. There were many things they needed to find out. How big was the magma chamber deep underground? How widespread would the effects of an eruption be? And crucially, when would it happen? To answer any of these questions, volcanologists knew they first had to understand Yellowstone's mysterious magma chamber.
It's incredibly important to understand what's happening inside of the magma chamber, because that pressure and that heat and that fluid is what's triggering the final eruption. It's like understanding the primer in a bullet.
Understanding the magma chamber would be very difficult. Smith and his team needed to discover the size of something 8 kilometers below the ground. They began harnessing information from an ingenious source: earthquakes.
Well, what we have here is a seismometer. This is the working end of a seismograph, the device that's used to record earthquakes. It is able to pick up the smallest of earthquakes in Yellowstone, plus it picks up moderate to large earthquakes around the world. It is so sensitive.
Like many thermal areas, Yellowstone has hundreds of tiny earth tremors each year. They are harmless. But in his seismographic lab, Smith has been using them to trace the size of the magma chamber.
Earthquakes are essentially telling you the pulse. They tell you the real-time pulse of how the caldera is deforming, of how faults are fracturing.
Bob Smith's 22 permanent seismographs are spread across the park. They detect the sound waves which come from earthquakes deep underground. These waves travel at different speeds depending on the texture of what they pass through. Sound waves passing through solid rock go faster than those traveling through molten rock or magma. By measuring the time they take to reach the seismographs, Smith can tell what they've passed through. Eventually, this builds up a picture of what lies beneath the park.
The magma chamber, we found, extends basically beneath the entire caldera. It's maybe 40 to 50 kilometers long, maybe 20 kilometers wide, and it has a thickness of about 10 kilometers. So it's a giant volume. It essentially encompasses a half or a third of the area beneath Yellowstone National.
The eruption here 3,500 years ago, although not VEI-8 in scale, did have a small magma chamber. Professor Steve Sparks has spent much of his career studying Santorini.
When I first came to Santorini and started to look at the pumice deposits from these caldera-forming eruptions, I found evidence of a dramatic change in the power and violence of the eruption.
By examining the layers of Santorini pumice, Sparks discovered magma chambers could erupt with almost unimaginable force and spread their devastation widely.
There's dramatic evidence of a sudden increase in the power. Huge blocks, about 2 meters in diameter, were hurled out of the volcano, reaching 7 kilometers and smashing into the ground. And to do that, the blocks must have been thrown from the volcano at hundreds of meters per second, about the speed of Concorde. And you can imagine this enormous red rock crashing in and breaking up on impact.
To understand why caldera volcanoes could erupt with such power, Sparks replicated their violence at 1/1,000,000th of the scale.
Okay, so we need this.
In the lab, he modelled the reaction which occurs in the magma chamber of an erupting caldera.
Yep. Problem is we can't go into a magma chamber, so the next best thing to do is to go to the laboratory and try and simulate what happens in the magma chamber and in the pathway to the surface.
Sparks believed escaping volcanic gas trapped in the magma might be responsible for the violence of the eruptions. Into a glass flask, the magma chamber, he poured a mixture of pine resin and acetone. The pine resin mimicked the magma. The acetone modelled trapped volcanic gases like carbon dioxide and sulfur dioxide.
Pine resin is a very sticky, stiff material, so it has some properties which are rather like magma. And we thought that if we could get a gas which dissolved in pine resin, like acetone, then we could get a laboratory system which would represent the natural case.
Sparks then created a vacuum above the flask to mimic the depressurization that occurs in the magma chamber. When a supervolcano begins its eruption and the dissolved volcanic gas can expand, when the vacuum reached the liquid, it caused a dramatic change. The dissolved acetone suddenly became a gas. This made the resin expand, causing violent frothing and blasting the contents out of the chamber.
These experiments give us tremendous insight into the tremendous power of gases coming out of solution and able to drive these very dramatic explosive flows.
But experiments in the laboratory cannot answer the biggest question of all surrounding Yellowstone. When will it next erupt? Scientists face a problem. They have never seen a supervolcano erupt. Until a VEI-8 eruption is observed and analyzed, no one knows what the telltale precursors would be to a Yellowstone eruption.
Nobody wants to see a global disaster, of course.